Shortly before 1 o'clock in the morning, on 14 June 2017, a fire broke out inside a fourth-floor flat at Grenfell Tower in North Kensington, West London. It started with an ordinary household appliance, a fridge freezer in flat 16. Within minutes, flames reached the window. Then something happened that the building's fire safety strategy was never designed to allow. The fire began climbing. Flames raced up the outside of the tower, spreading across floor after floor and re-entering apartments higher above. By morning, 72 people had lost their lives. But the most important question is not simply why the cladding burned. It is how a fire that began inside one flat was able to bypass a building designed to contain it. Because Grenfell's safety strategy depended on one fundamental idea: the fire was supposed to stay where it started. To understand what happened, you first have to understand how a high-rise residential building is supposed to behave during a fire. It is not designed as one enormous open structure. Each flat is intended to function as a separate fire-resistant compartment. Concrete floors, walls, and fire-resisting doors are designed to slow the movement of fire and smoke, giving occupants of the affected flat a chance to escape while protecting people elsewhere in the building. This principle is known as compartmentation, and it explains the logic behind Britain's traditional stay-put strategy. If a fire is contained inside one flat, residents in other flats are generally safer remaining inside their own compartments than attempting to evacuate through a shared staircase. Grenfell Tower had only one staircase. That meant the strategy depended on a simple chain of events. The fire stays inside the flat. The compartment contains it. The staircase remains usable. Firefighters deal with the fire. It was a system built around containment, and for that system to work, containment had to hold. Between 2012 and 2016, Grenfell Tower underwent an extensive refurbishment. New windows were installed, heating systems were upgraded, and the tower's exterior was transformed with new insulation and a rainscreen cladding system. From inside the flats, much of the original structure appeared unchanged. The concrete floors were still there. The walls were still there. The single staircase still ran through the center of the building. But outside, the building had acquired something it had never previously possessed: a continuous layered façade system capable of carrying fire vertically along its exterior. The rainscreen system used Reynobond 55 PE aluminium composite panels, known as ACM. These panels consisted of thin aluminium sheets surrounding a polyethylene core, a combustible plastic material. Behind them were combustible insulation products and a ventilated cavity. That cavity was not supposed to become a route for fire. Fire-stopping cavity barriers were intended to interrupt the space and restrict the movement of flames and hot gases. But the Grenfell Tower inquiry found serious problems with the external wall system, including inadequate cavity barriers and problems with their installation. The result was a dangerous combination: combustible materials, a continuous cavity, and inadequate fire stopping. The concrete compartments had not disappeared. The fire simply no longer needed to pass through them. It had been given another route. So how did such a system end up on a 24-story residential tower? The Grenfell Tower inquiry found that the answer could not be reduced to one contractor or one bad decision. The failures stretched across manufacturers, testing organizations, designers, contractors, building control, and the regulatory system itself. The rules governing external wall construction were not sufficiently clear, and responsibility for understanding the fire performance of the completed wall system became fragmented. During the refurbishment's value engineering process, the original cladding specification was changed to an aluminium composite material with a polyethylene core. Cost was one factor in that decision. At the same time, the inquiry found serious failings in the way some manufacturers tested, marketed, and presented information about their products. Individual products could appear acceptable in isolation, while the completed wall system created a very different fire risk. And no single point in the chain adequately stopped the completed façade and asked the most important question: what happens when all of these materials are installed together on a high-rise building? That question mattered because fire does not experience a building as a collection of separate contracts. It experiences the building as one physical system, and the completed façade created a system that could spread fire rapidly. But the external wall was not the only part of Grenfell where protection was compromised. The inquiry found that many of the flat entrance doors installed during the refurbishment did not provide the required level of fire resistance. Some self-closing devices were also defective, damaged, or missing. There were problems with fire stopping around parts of the building as well. These failures mattered because compartmentation was never just about concrete. It depended on doors, walls, floors, service penetrations, and fire stopping working together. So by 2017, Grenfell's fire strategy contained weaknesses both inside and outside the apartments. The system still looked like a collection of separate protections, but those protections were not as reliable as the original strategy assumed. Then, shortly before 1 a.m. on 14 June, the fridge freezer in flat 16 ignited. Firefighters arrived and entered the fourth-floor flat to deal with what initially appeared to be a contained domestic fire. This was exactly the kind of incident compartmentation was designed to handle. Then the flames reached the window. They encountered the external wall. The polyethylene core of the ACM panels ignited, and flames began spreading rapidly across the façade. The fire traveled upward, sideways, and around the building, reaching flats far above the original fire. Flames also re-entered apartments through windows. The direction of fire spread had changed completely. It was no longer simply moving through the interior of one compartment. It was moving across the outside of the building and then back inside. The concrete floor slabs could still perform their intended structural function, but they could not stop a fire traveling around the outside of the façade. The building's containment strategy had been bypassed. Inside the tower, the consequences became increasingly severe. Smoke and fire began entering flats that had not been involved in the original fire. Residents who had initially been protected by the logic of compartmentation were now facing conditions that strategy was never designed to handle. The London Fire Brigade continued giving stay-put advice for a significant period because the established doctrine was based on the expectation that fire would remain contained. But the building was no longer behaving as a collection of isolated compartments. The fire was spreading externally and re-entering flats on multiple floors. The operational problem was now fundamentally different from the one the original strategy assumed. By approximately 2:47 a.m., the stay-put advice was formally abandoned, but by then, the single staircase was heavily affected by smoke, making evacuation extremely difficult. A strategy designed around containment was now being used in a building where containment had already been breached. In September 2024, the Grenfell Tower Inquiry published its Phase 2 report, completing its investigation into the circumstances surrounding the refurbishment and the disaster. Its findings revealed a chain of failures extending across the construction and regulatory system. The inquiry identified the ACM panels with polyethylene cores as the principal reason the fire spread so rapidly across the building. But the panels were not the whole story. Combustible insulation, inadequate fire stopping, defective fire doors, weaknesses in testing and certification, failures in regulation, and a fragmented chain of responsibility all formed part of the wider picture. The disaster was not the result of one isolated mistake. It was the consequence of multiple failures interacting within a system that was supposed to prevent exactly this kind of catastrophe. And this is where Grenfell becomes more than a story about cladding. The concrete structure did not collapse. The fire service did respond. Compartmentation itself was not an irrational idea. The problem was that multiple protections depended on the same underlying condition. The fire had to remain contained. When the external facade gave the fire another route, that condition disappeared. The consequences traveled through the rest of the system. The stay-put strategy became unreliable. Evacuation became harder. Firefighters faced a type of fire behavior that the original strategy had not anticipated. Residents who believed the building was divided into protected compartments were suddenly exposed to fire entering from outside. None of these failures existed in isolation. They interacted, and that is what makes complex safety systems dangerous. A protection can appear independent while actually depending on the same hidden assumption as every other protection around it. If that assumption changes, several safeguards can become ineffective at the same time. 72 people lost their lives. Grenfell Tower exposed weaknesses that extended far beyond one building, triggering a national examination of high-rise construction, fire safety, and building regulation. But its deepest lesson is broader. A safety system can contain dozens of safeguards and still remain vulnerable if those safeguards all depend on the same assumption. The danger is not always the thing that breaks. Sometimes the danger is the thing everyone assumes will never change. Grenfell's fire did not simply break through the building's defenses. It found a route around them. And once it did, a system designed to contain one fire began confronting an entirely different reality. That is where complex systems can fail. Not when every component breaks, but when reality changes faster than the assumptions protecting us. If this investigation changed how you think about the systems around you, subscribe to Null Theory for more cases where the real failure was hiding in plain sight.